In the last class, what we saw about the conservative, non-conservative forces and the work energy theorem and all, right? We saw work energy theorem. So in this class, in this lecture, we will see about the conservation of linear momentum. Actually, it's nothing like that. Because, see, if you remember in Newton's second law of motion, what is Newton's second law of motion? Momentum. Yeah, what? The rate of change in momentum is equal to the external force applied, right? So what it says is, so your force, it's proportional to, remember, proportional to, but we said that by using a proper units, we can remove the proportionality constant. So we can write the force, Newton's second law states, F is equal to dP by dt. Okay. Now you tell me, so if this is an external force, remember it's important, huh? External force. I will come why it is important is. Well, so now if there is no external force, so then what happened? If there is external force, then what will be? dP by dt will be? dP by dt will have what? When there is no external force. When there is no external, will be 0. 0. Very good. Okay. Do you remember? If you have done the differential calculus, dy or dy by dx is equal to 0. That means y will be equal to a? 0. Constant. Correct. Constant. Okay, you should remember. Constant. Right? So, then same way, then what this will be? Momentum will be a constant. Correct? That means momentum will not change. Okay, and that's what your conservation of linear momentum. In the absence of any external force, the momentum will remain constant. It is not just for a body. Okay, if there is no force acting on, the body will remain. Suppose in a space, if you go, you keep a ball or whatever it is, it's going to remain there only. Okay, if it's moving at a constant velocity, it remains at a constant velocity. The momentum, because there is no force, the momentum will be always conserved, not change. Okay, and we will come to that. Okay, so then, but this is not only for a single object. It's for a system also. What do you mean by system? Okay, system of objects. Okay, what they call is an isolated system. Okay, so what the system means? Okay, let me take out. For example, you are having well, how can I put example? Okay, let us take an molecules in a box. Okay, so what will be the molecules in a box? I'm going to air in. I'm having a box. Okay, and there is a air in the box. Okay, so for example, the molecules are very lightweight, so gravitational force you can neglect. That's why they are all freely moving. The box is stationary. Okay, so that means this is at rest. There's no external force acting on it. Okay, but if you see the individual molecules inside, they all are moving. Okay, they are moving, they are colliding each other. Okay, so when you say this collection of molecules in the system, that is a system in the board, this is a system. Okay, so when you see that as a whole, there won't be any net change in momentum. You got it? It is not going to happen. All these molecules are coming and hitting on the wall and push this at one side. It's not going to happen. Okay, the net momentum will remain unchanged. Even the individual particles are moving as a net, the momentum will remain unchanged because there is no external force acting on it. Correct? So it is not only for an individual body, it's for the system of particles also, system of bodies or something, it's for a system also. Okay, so this type of system, when there is no external force acting on it, so that is what you call as your isolated system. Okay, it's not just this. Take a firecracker. What do we have? We have a firecracker. Am I right? So we have a firecracker, something like this. It's not a nuclear bomb, it's a firecracker. Okay, so what are you going to do? You are lighting we light it, right? So after some time, what happened? It bursts off. And all the particles will be thrown out. Okay, is there any external force acting? Is there any external force acting on the system? This all is a system, right? Because it's a one single system. Is there any external force acting on a system? But there is a momentum, things are moving.
Moving on its own because of the heat energy.
Energy is there, but if you see the net momentum, okay, the net momentum, because this is like one direction, this is another direction, opposite direction. This is a positive direction, this is a negative direction. When you add up all of them, they will become zero.
Okay, so it will be constant.
It will be constant. Okay, so because why? There is no external force acting on it. Whatever the force acting on the body, there is the internal force, the internal energy, which cracked. Well, but if you look at this only one piece, if you want to look, then there is external force acted on it. That's why it's moving. So when I do individual, when I see a piece, of course there's external force acting on it. But when I see as a whole system, there is no external force act on it. So, and if the system is an isolated system, something like a exploding firecracker, okay, then you can say there what is that? The momentum will be conserved because there's no force acting on it. This form will be there. Okay, so that's what they written as your isolated system, and this one. And then actually after that they have the line is this: the total momentum of an isolated system. Okay, the total momentum of an isolated system is conserved during any interaction. Any interaction going through it, the cracker is bursting. Okay, whatever it's happened, the total momentum of the isolated system will be always conserved. Conserve means if it is at rest, it will be at rest. If it is moving, even if it's a net collection of momentum, all those things, if you add up, they will have same momentum. Okay. So this is what about your total some momentum conservation. Okay, and then there is something they given, mathematical approach for the application of Newton's second law. But anyway, I am not very clear what they have written. Okay, but let me put it in my own way. Fine. Okay, that's right. What they said is, see, so if you have a system, okay, this I made as a very complex system kind of thing. But let us not go for a complex system. Let us take a simple system. You are in a well, you are pulling a pulley. You know the pulley, right? The bucket of water. Okay, so you are applying a force. Now, if you see in the bucket, what is that we are having? Let me draw it. So, what we are having a well. Okay, and then there is a pulley. And there is a bucket of water. And you are pulling it from here. The water is moving up. Okay, so now, so this is a system, pulley and a weight system. Okay, so this is a system. Now you have to find out what is the, what is the acceleration of the rope you are pulling? What is the acceleration of the bucket which is moving upwards? So these are the system. Okay, so now if you ask all those questions, how we are going to find out is just calculate the force. Am I right? Just calculate what is the net force. Suppose if you want to know what is the acceleration, can you tell me what is the acceleration? The bucket is moving up. How do you find out? Calculate the net force. All you do is the net force. Then Newton's second law says force equal to mass into acceleration. The net force divided by the mass will give you the acceleration. Okay, so otherwise what you have to do with the acceleration, you have to find out the velocity, take the derivative of the velocity, dv by dt. Correct? Because if you remember what we had, velocity v is equal to dx by dt. Am I right? These all are vectors. And a is equal to dv by dt, or that we can write as d square x by dt square. Correct? Second derivative. So that's what you can do. But here what happened? You find out the force. What is the net force acting on it? And just divide by its mass, you get the acceleration. So this is what a matter of application of your Newton's second law. So let us take some system of a pulley-based system. What they given in the book is a pulley-based system. Okay, I will give a pulley-based system, and then let us see how we are going to find out the acceleration of different part. They given a very complex image. Okay, but anyway, I will tell you part by part. But anyway, in your, I don't know, in the book, however they given a complex, there are some mistakes also, and we will see how we can do it about it. But the questions are simple, but they only The figures they give, I don't know why they give a complex figures. Okay. See, okay, let me draw what is the figure they are given. This is what's the pulley, the system they given in your book. Okay. So what it says is these are the pulleys. So let me call these pulley names as, okay, let me call this as P1, P2, P3 and P4. There are 4 pulley systems. Okay. And what they have done, this is a string. So the string neglect the mass of the string. There is no mass of the string. Okay. And it's not extendable. It's a fixed. It's not a rubber band. Okay. It's a non-extending string. Okay. So if you connect, if this is the way, that means you are connecting 2 masses here, 1 kg and 2 kg. And total 3 kgs here. And now if you, and this 1 kg and 2 kg is not going to make a difference because the total load will be 3 kg. However, the tension on these wires is going to be different. Okay, so we have to find out those things. You will see that. Okay, effectively it will be all same. And then this is another pulley from where you're hanging up 3 kg, and then that goes through another pulley, and they got a 4 kg. Then comes to the pulley, and then you are tied up with a 5 kg block, and then you are having a rope, and you're pulling at a 100 newtons force. Now, see, this is have a friction. Am I right? So the 5, because on the platform it is moving. The frictional, when you pull it, the frictional will opposite force. So the opposite force is 10 newtons. So now we have to find out what is the acceleration of different components. You can actually find out. Okay, but I don't know, in this book they are not used for this, but this is not very simple to find out acceleration of different masses. If you're asking what is the acceleration of different masses, you can actually find out. Okay, so let us not go into this one. Anyway, in the book they have not solved it also. So, but I will tell you take out the simple part of the pulley, and if I ask you what should be the acceleration, we can find it in a very simple way. Okay, so let me do that. So what am I saying is, if for example, let me take this part of the system. Okay, let me try to see. So what am I going to have? I'm having this is a okay. Take out this system of pulleys. Now I am asking you a question. If I pull the pulley by some distance, okay, what am I going to do? I am going to pull it from here to here, okay, by a distance x. So let us say this is fixed, for example. This side is fixed. What am I doing? I am pulling this rope, the string, by a distance x. Can you tell me how much? So this is going to move up? How much this will move up?
What will be the mass without it?
Okay, take out any mass, doesn't matter. I'll tell, okay, this may be some 5 kgs. Okay, you put up 5 kgs. Doesn't matter, doesn't require. Okay, how to do it is, okay, suppose, will it move by x or something less than x? Can it? Less than x, correct? So that's you have to know it. Okay, so now only thing, it move less than x, but you don't know how much it. Okay, so what am I going to do? I am going to remove this also. Okay, so let me call this side moved with x1 and this one I am moving by x2. So then what happened? So suppose if initial length is L. Okay, let me call this initial length. Initial length, when it is here, the length is L. Okay. Now after pulling by this string by x1 and this string by x2, the length will be reduced by how much? Now the new length L prime will be L minus These two, x1 plus x2. Okay. So now, so this is the new length. So the pulley will be at the mid of this new length. This both side has to be same. So your new length, okay. So your this is L prime. Okay. So this new position, what I call. So this position initially it was x, or maybe some distance. It has by moving it up to here. Okay. So this will be. I shouldn't write it as L. Let me call it as 2L. L is this length. Am I right? This is a total length. Na? So now 2L prime will become this. Therefore, L prime will be how much? Tell me. L minus x1 plus x2 by 2. Correct? You got it? I took it as 2L prime because I am not taking the total length. I am taking this length as L. So initially the length was L plus L, 2L. Now after I pulled by x1 plus x2, the length reduced to L prime, 2L prime. So become 2L prime will be the initial length L minus x1 plus x2. So therefore, now the new length L prime. L prime is this height. Am I right? The L prime will be, that means just I divide by 2 everywhere. L prime will be L minus x1 by x2. So if I take this one here, okay, so then what happens? Or I can take this one here, L minus L prime. Okay, so let me write it. So what happens? So then, because of course L prime is smaller, right? So L minus L prime will be how much? Tell me.
x1 plus x2 by 2.
You got it? So now you got it. So now when I move this by x1, I move this by x2, how much this will move up will be x1 plus x2 by 2. Clear? Now what am I doing? I am fixing this. That's what my question. Am I right? Now I am fixing this. Now I am pushing by x.
Will be x1 by 2.
Yes, correct. X1 by 2. But now what happened? Now if I change what I made, my x1 is equal to x, x2 is equal to 0. So my increase in length will be x plus 0 by 2. So my change in length, the movement pulley will be x by 2. This moves up. Okay. And so this is the way you can solve it out. Okay. And now other interesting thing is, if you know to solve this way, you can actually find out your acceleration also. For example, let me fix up this one. I am pulling it. It's initially at rest. Now I am pulling the string with some acceleration. Okay, that means what? I am going to put a mass, heavy mass. The mass is going to pull it down. So it's going to, so this mass is going to move down with some acceleration, and this is also going to move up with some acceleration. Will the both acceleration be same? Again, it will be different. So now we are asking, so what will be this acceleration? If I call this acceleration, so what I have tied up a mass. Now what am I going to do? I am going to tie up a mass, say some heavy mass m. So now this is going to move down with an acceleration a1. So because this is going to move down acceleration a1, this is going to move up with the acceleration a2. Now if I ask you, what will be the, if a1 is acceleration, what should be my a2? Okay. You can use all equations of motions also. Yes. So you remember we had one equation, if you remember. S equal to ut plus half at square. Correct? Okay, so then just take out a time. Okay, anyway, here the initial velocity is 0. So we don't have anything like this. So what we are going to have S equal to half at square. This is the equation we use. So now what am I going to do? So let us take during a certain time t. This mass has moved down by a distance s. How much this distance will have moved by the time? Correct. How much? We just did.
Okay, s by 2.
Correct. So this will move up by a distance, in that case s by 2. Okay. During the same time, this has moved up by a distance s by 2. Okay, so let us write the equation of motion of this mass. So what will be? So S is equal to, there is no initial velocity, half, I said A1 T square. Let us write the equation of motion of this one. Tell me.
S by 2.
Correct. S by 2 will be equal to half A2. Time will be same because we are calculating the same time. Take out the ratio.
Okay. We can equate by.
Do it. Okay, so take this one, equate it. So what happens? So from here S is equal to A2 T square. Correct? So that will be what? A2 T square will be equal to half A1 T square. T square cancels. Therefore, A2 will be equal to half A1. The same way like where S also is 1. So if you move this one with the acceleration A1, this is going to move down the acceleration, half of it. Okay?
It will go twice.
Half of it. A2 will go half of A1. Na?
Okay.
Because this will move faster, this will move slower. Okay, this acceleration will be slower than this acceleration. You got it? So this is the way you can find out the pulley. You can actually, one way you can sort it out. But anyway, let me read what they have written on your book. Okay, and this is what they said. Consider the arrangement given. Okay, I'm not reading it. Okay, see, until there's a discussion they are given. Until 1 kg mass reaches the pulley P1. Okay, the motion of 1 kg and 2 kg masses is identical. Of course, they will move downwards. Am I right? Because if it crosses, then only 1 kg go that side. Till then, the 1 kg and 2 kg is going to be on one side only. So thus these two can be considered to be a single system of mass 3 kg. Except, what is that? Except for the knowing the tension T3. Yes, okay, they have written the tension also. Let me note down the tensions. Okay, the tensions what they have written is, so this is T3, this is T2, this also, the same tension is coming here, T2, and here also same mass and same tension. Am I right? So this is the same tension, the same mass is going to pull the tension, and the same tension carries over here. So up to here the same tension will be there. Correct? Yes. And then comes, you understand why I am making the tension? The single rope now, because it's a frictionless. So it is single, the same tension will be up to here, up to one mass. Okay, so it is, what I am saying is, it's something like that. You catch these two sides of the thread and you pull with the pulley there. Both the things is going to have the same tension. It is as equal to that. Am I right? So therefore, this whole tension is going to be same everywhere. Whereas here it will be different because the 1 kg mass is in between. You got it? And similarly for here. So here also this 4 kg mass is going to be between. So this will be T1. So this portion also going to be T1 because this is the same stretch. Am I right? So this is what the tension they are given. Okay, what they written there is, thus these two can be considered to be a single system of mass 3 kg except for knowing the tension T3. You got it? Tension is going to be different. Okay, the forces due to the tension and in the string joining the moral internal forces for the system. Of course, this all the way how the strings are being joining. The string is also getting a force. Okay, those are internal forces, not external forces. We are doing that. Okay, that's why we are saying this is not a stretchable string. It's a fixed. It means the rigid string. You can say call it. Fine. Okay, and then one more thing they got, all masses except 3 kg mass are traveling in the same same distance in the same time. That's also not completely true. Okay, I don't know, this is wrong. Okay, so of course, no, if I move it out, this may not Okay, it's not, I don't know what they meant by there. Does their acceleration, if any, have the same magnitudes? No. So wait, I don't know why they written this. If the string is connecting 1 kg, yeah, okay, if this is a string 1 kg, I think so, and 4 kg mass, yeah, this too, okay, moves by x, if you move it by x, okay, the lower string S1 loading the 3 kg mass, that will go by x by 2. That way, anyway, it did it. Okay, you got it, na? Moves through x by 2. Anyway, the way they written is very badly they written, and some of things are not wrong. Okay, acceleration not going to be same. Okay, if you pull it here, it's not going to be same acceleration there. Okay. Well, so this is what the thing is. So now let us come back to the Newton's second law of motion. So how we are going to find out the acceleration? So for given a system, something like this. So let me remove this one. Okay, let me go to the figure what they given in your book. Okay, and let us try to find the acceleration or of a individual objects what you are moving. Okay, I mean maybe 2 kg, 1 kg, 3 kg, 4 kg, 5 kg, how they are moving, we can find out what is the acceleration. Okay, so what they do is, okay, fine. So now if I wanted to find out what is the way these masses are moving out, acceleration. So one of the convenient figure what you call is a free body diagram. What do you mean by free body diagram is, suppose if I wanted to find out the more acceleration of this mass 2 kg, just pick up that. Something like remove everything. Suppose just look only this and see what are all the forces acting on it. What is the direction of the force? Okay, and so by that you can find out a net force. Correct? So if there is a net force is in any imbalance, then the object is going to move. It's going to have it's got an external force. Okay, so when you can make an image of that, that's what's called as your free body diagram. What is that? Free body diagram. So let me write one. Free body diagram. What is free body diagram? I said, take out a one. Okay, let me read what is it in the book. Free body diagrams. A free body diagram refers to forces acting on only one body at a time and its acceleration. That's what I said. Okay, take up the one body and all the forces acting on that body and its acceleration. When you represent only that, then it gives you the free body diagram. Okay. So now let us see what it is, the free body diagram of the 2 kg mass. 2 kg mass. Okay. So they given, let A be its upward acceleration. Okay, some acceleration. They mentioned it's upward, but you don't have to make it upward, maybe downward also. All depending upon, of course, here when you pull it up, this may go upward only. Okay, so upward acceleration. So what they given, so free diagram of 2 kg mass. What you are going to do, free body, not free diagram, free body diagram of 2 kg mass. What will you do? So in the free body diagram of 2 kg mass, how you are going to do is, let me draw the 2 kg. Okay? What all the things will happen? What are the forces acting on it? First one, there is a force which is going to gravitational force. That will be 2g because mass is 2. Am I right? Correct. So 2g is going to act downwards, and then I will tell you. Okay, and then
2a because
A's acceleration is there, but there is another force acting on it. First, you make what are the all possible. See, A actually in the actual problem, you have to actually find out the A. So we have to find out what are the total forces acting on the body first. Okay, so what are the total force? Other force what is acting? The tension. Of course, it's not it's not on the air. It's not just falling down. There's a tension, right? Tension act upwards. T3. Am I right? So in a book they given what they say is you make a cross. Something like this. Okay? And then you divide it. So that means this portion means it shows a tension upwards. This body will face it upwards. This body face it downwards. You got it? So they given that. Anyway, that's okay. You can do it. Fine. So, so is there any other force acting on the body? 2 kg?
Pulling force, that will be E, right?
That's what is going to give an acceleration. That's what you have to find out. Something. Okay. So there won't be any other force. Am I right? Because only this one 2 kg is going to pull it down, and this tension of T3 is going to be upwards. Okay. And then whatever the pulling, that's going to pull this force here. So the net force, what they have written is, yeah. So the net force, if A is the acceleration, let me check a different color. So let me take up a different color. So if A is the acceleration, it's moving up. Okay, then the force, the net moving upward will be equal to 2 times A. Am I right? Wait. So now can you say what will be the equation will be? The resultant force is T3 minus 2G will be equal to 2A. Is that correct? That's what your free body diagram is. Okay. If I want to find out acceleration, if we know the tension, if we know the mass of the body, acceleration can be just divided by this divided by 2, the mass of the body. There's one example, we will do that. Okay. So this is what the free body diagram for a 2 kg mass. Now let us see, they have given one more thing also. So the free body diagram, okay, let me read it. The free body diagram of a 2 kg mass, let A be its upward acceleration. According to Newton's second law, it must be due to the resultant vertical force on its mass. Correct? So to know this force, that's what, to know this force, then only we can find out the acceleration. To know this force, we need to know all the individual forces acting on this mass. You got it? So the agencies exerting forces on this mass are Earth's download force, gravitational force, and the force due to the tension T3, which is pulling it up. Okay, there are only 2 forces acting. So that means one is 2G, another one is tension T3. Okay, so if the tension is higher, go upwards. If 2G is higher, it will move, it's larger, sorry, if it's larger, it moves downwards. Okay, fine. In this case, the lower half of the string is connected to the 2G mass, correct? The string is connected to 2G mass. Okay, and interestingly what happened, when you look for 1 kg, this T3 will give a downward force.
Okay. So you give a downward force additional to the gravity.
Additional to the gravity. Okay, and this one will give an upward force. So that's what, for example, okay, well, if I want to draw this free body diagram for 1 kg, what is that you are going to get? So 1 kg, it will have one force which is G, because 1 into G. Okay, and the another one is T3, and the upward force will be T2. So this is the free body diagram. Okay, so then what happens? Then you can write your T2 minus T3 minus G, 1G, right? That will be equal to 2 times your acceleration. Because, sorry, 1, mass is 1 kg, na? Sorry, yeah. Will be your A. You got it? So this is free body diagram for this 1 kg. So, but however, that doesn't matter for 2 kg. Because what matter going to 2 kg is only this is going to pulling upward force. Okay, so that's where written is. The direction T3 for the lower part of the string is upwards as shown in the figure 4.2b, yeah. Okay, upwards, the lower part is. Okay, the upper part of the string is connected to the 1 kg mass. Am I right? Thus, the direction of T3 for the 1 kg mass will be downwards. Am I clear? Am I making clear? However, it will appear only for the free body diagram of 1 kg. This downward force will appear only for the free body diagram of a 1 kg. But it doesn't matter for a 2 kg. Okay. It will not appear in the free body diagram of 2 kg. Hence, the free body diagram of 2 kg mass will be as follows. This is the one they given. T3 minus 2g equal to 2a. You got it? This is the way you have to write down the free body diagram. And now, they give one more. Suppose the free body diagram of a 5 kg. Okay, now 5 kg is interesting. Why? Because there are a lot of force and different component force are there. Am I right? So let us write down the 5 kg. So what you are going to have, so this is the 5 kg. I am not going to have anything. I just draw only the 5 kg. Okay, and we are actually pulling it along certain direction. Okay, and that is your F, which is your 100 Newton. Let us keep it F only. Now, when you make a free body diagram, you don't make arbitrary force directions and all. Everything resolved into rectangular component. Okay, so it's given. So they have said, this is how, what is the angle? 60 degrees. So now you can resolve this force into two components. Can we do it? So tell me, what will be this force? F cos 60 degree, and this will be F sin 60 degrees. So this force we have accounted for it now. Now, of course, 5 kg, it's going to have a gravitational force also.
5G.
So that will be 5g, that will be moving downwards. Correct? So all possible force you have tried down.
Tension force.
Yes. What's the tension force?
Tension force and the friction force.
Yes, exactly. Very good. So tension force is what? T1, right? So here there is a one tension which is going to be T1, and then there's a frictional force. So since you are trying to pull this side, the frictional force will be also opposite side. So that's also going to be frictional force. So let me, what is the symbol they have written? Well, opposing force, they are not at any symbol. So they put it as 10 newtons, right? So let me call that opposing force as F or small f. Small f OPP. Basically, it's the frictional force. Okay. Is there anything else I missed? Any other forces left over? No, correct? Everything we have considered. So that's all the end of the free body diagram. So now you can actually remove this. You don't have this. You don't need this one. The exam you draw it. Okay. So this all. And now everything you have to balance. So is the body moving upwards? So that means these forces should cancel. Yeah. One more thing. I missed it. There's one more force is there. When you put a mass on the table, yes, opposite reaction force. Okay, the third law will happen. Where this is going to put a force 5 kg on the table, and the table will exert a 5 kg on the mass. So that will be also in the upward direction. That you call as a normal reaction. The normal reaction is what? Because of the Newton's third law. Because the body is applying a force on the object, so the object will apply a reactive force on the object. That is your normal force. You got it? So this is what it completes. Okay, so we missed this. So now we can see. Now in the vertically, you got all the vertical forces, upward and downward forces, and horizontal force also. Now you calculate. Take the net. If you have any net vertical force, okay, of course, vertical force will be only above. Okay, though if this force is higher, then the object will start moving upwards. If this force is higher, then the object will moving sidewards. So the resultant, the object will start moving along a line. Okay, but by chance, if your force, the object is not able to move upwards. That means 5G is balancing these two forces. It can be greater, I can say, it's balancing. So the 5G is balancing this combination of these two forces. So in that case, your free body diagram, it gives you, so it gives you, here I can write. So n plus F sine 60 degree minus 5g, correct? There's a force. Will be equal to what?
Zero.
Correct, 0. There's no force, na? That's it. So there is no horizontal motion. There is no vertical motion at all. Okay, so that's what they have written. Okay, they have written it's taken the 5g here. So n plus f sine 60 degree equal to 5g. They have written that. That's your first one along the horizontal. So this is along the vertical direction. Okay, so there is no motion. Now let us come back to the horizontal direction. So what are the forces we have? T1 plus F opposite force. Correct. Minus F cos 60 degree. Actually, we wrote it wrong because there's accelerations happening this side. Okay, so yeah, F cos, this is the larger force. Always, if then always you have to write the acceleration as a negative acceleration. Okay, so what happened? So you have to write F cos 60. That is the force which is pulling the 5 kg because you have taken F equal to how much? 100 newtons you are given. Okay, so F cos 60 minus T1 minus F op will be equal to 5 times the acceleration A. You got it? So, okay, I don't know why they have written it. 5 times the acceleration. Okay, and I am not sure why they have done like this. Okay, I don't know. What they have said is what the answer they gave is for equilibrium. That means you are holding with a force such that nothing is moving. Okay, so when nothing moves, what I call when equilibrium, when you're moving it up, then what happens? Then this acceleration becomes 0. Am I right? So when this becomes 0, so what we have, that's what the answer they gave it for in your book. Yeah. So then T1 plus F opposing force, let us call it as 10 newtons. That's what you are given, right? 10 Newton will be equal to F cos 60. That's what they given in your book. Okay, and then I don't know why they wrote it as equal to T cos 60. I don't know what the T they call about. Are they calling it as the total tension? What is the T they are saying? Yeah, they can be. That is the total tension. T is, they are not mentioned anything. Because see, this is the force. What you are holding, this is the force which is accounting for the entire tension. Am I right? So this will be what? So this, so and they returns T cos theta. I don't know. It's not T cos theta. So you have to basically add up all the tensions. But this is the certain way holding it. So this causes the motion of all, everything is a step equilibrium. Okay? So reaches an equilibrium. Equilibrium means nothing, no motion, nothing is going to move. Fine. So, okay, similar equations can be written for all the masses and also for the movable pulley, of course. Movable pulley also you can move. That's something but acceleration we said, na? Pulley. On solid equation we can, okay, fine. Okay, so then they given an example for 0.5. Usually I don't do the example, I will toss the example for you to do, but this is an important example. So let me do it. Okay. So this is called as the Atwood's machine. So with that I will stop. Okay. So let us do this problem. This exercise, what example what they given. So this is what you call as Atwood's machine, where you connect the masses in a single pulley. Okay. So what says is, figure shows a fixed pulley, okay, a massless inextensible string. String doesn't have a mass and that cannot be extended, okay, is with masses m1 and m2. attached. Okay, and the given M2 is larger than M1. Attached to its two ends, both ends of the string, and passing over a pulley. Okay, such an arrangement is called as a Atwood machine. Atwood. Okay, Atwood machine. Okay, Atwood machine. Calculate the accelerations of the masses and the force due to the tension along the string. Assuming the axle of the pulley to be frictionless. So this is a freely moving pulley. This is an okay. So what you have to find out? You have to basically find out the tension and the acceleration. So the method is what? You remember in your book they given, you can follow the same way. Just put a cross. Am I right? So the tension. So there will be a same tension because two masses have the same tension. So this tension here it will be acting upwards. For here it will be acting downwards. This will be tension, right? The arrow says this is upward and downward. From here it will be downwards. You're pulling it. For this mass it will be like a pulling. For here pulling, but for this mass it is basically pulling up. Okay, here also it is pulling upwards only. Okay, but for the pulley from this part of the string, this tension is downwards. You're pulling it. Okay, fine. So that's what you have to make the mark. Yes, so now they in a book they given two methods. Okay, so let us try to follow the same method. Okay. Okay, fine. So now they given M2 is greater than M1. So where will be which force will be more? This will pull it down. Am I right? So the net force will be this force minus this force. Am I right? So let us do the method one. So the net force acting on net downward force. F will be M2 times G, am I right? Minus M1 times G, or I can write it as M2 minus M1 times G.
Will it be G or will it both the tension also give it a opposite pull?
Tension will be the same. That you have to find out, na? It is not stretchable, na? Okay. You want to go for the free body diagram. We will do the other method. This is one method we are doing. The second method we will do exactly. You are quite good. So we will take a free body. That's what you call the free body diagram. Take out the mass separately and do that. We will do that second. So in the book they given both the methods. First we are going to do the direct method. Next we will go for the free body method. Okay. So M2 minus M, this is the force acting on it. Okay. So now what's the total mass of the system? Total mass of the system is what? Plus M1. Mass has to be added only, right? So total mass of the system equal to M2 plus M1. Now you know. Force equal to mass into acceleration. Okay, so F will be equal to M into acceleration, or acceleration equal to F by M. So F is equal to what? M2 minus M1G divided by M2 plus M1. Okay, therefore acceleration equal to M2 minus M1 divided by M2 plus M1 times G. Okay, so this is what the acceleration. Now we found out the acceleration. What the next thing we have to find out? Tension. Tension you can do it simply because take out, suppose for example, both the side tensions are going to be same. A single string. So tension is what? Because there will be downward force. Okay. And then upward is a tension. And that resultant will cause an acceleration. That acceleration we have. Correct. So we can do it. Nah? Simple. Tell me. So what will be that? So here the downward force will be what? M1G. Okay. The upward is tension, right? So maybe here this is going to move down, so this is going to be larger. Am I right? Because M2 is larger. So then what happened? T minus M1G. Am I right? Tension minus M1G is going to be the force, acceleration force, right? That will be what? M1 into acceleration. Right? That's the force, resultant force, na? Because F equal to mass into acceleration. So this is the resultant force which is going to happen. So from there you can find out, na? So what is that? Tell me. T is equal to
A minus M1 plus M1G.
take M1 common, na?
M1 equal to A plus G.
M1 into A plus G.
A we can substitute from there.
Correct. A you can substitute from there. So you can go and do it out, whatever it is. Okay. So you can do it out. So you want to do that? So tell me. M1 into A. Let us put the A here.
2 minus M1
M2 minus M1 divided by M2
plus M1.
and G is there. I'll take the G commonly outside, so it becomes 1. Can I do like that?
So M1G.
Now tell me.
So M1G into equal to M1G into M2 minus M1 plus M2 plus M1. So 2M2 divided by M2 plus M1.
Tell me. So this cancels off.
M2, 2M2 will come.
2 M1 M2. Correct. This M1 is also there, na? So what you're going to get is 2 times. This is going to give one M1 and this will give you one M2 by 1 plus M2 into G. That's what your tension is. Now let us go for the which one? Free body diagram. Shall we use the free body diagram and do this whole problem? Anyway, almost we did that only here. Okay, so let us find out the acceleration also using the free body diagram. Okay. So how we are going to write the free body diagram? We have to draw the free body diagram for both the masses. Okay. So let me take for the mass M1. There will be, what are the forces acting? There will be a downward force acting. That will be M1G. And there will be upward force acting. That will be a tension. There can be resultant force. Actually, that's right. And similarly for M2, what it will be? Tell me.
M2G.
M2G. And upward force will be a tension T. Correct? So now, let us write down the, of course, they both are going to have the same acceleration. Correct? So now, so let us write down the resultant force for this. So of course, since M2 is larger, so T will be larger than M2G and M2G will be larger than T. That's why this is moving down, this is moving upwards. Correct? So then what happens? So your T, oh sorry. So T, so D is larger, right? So T minus M1G. That will give you, that will be the resultant force, right? So that is going to give an external force, acceleration. So that will be equal to what? Tell me. A or M1A?
Okay, M1A.
This is a force equation. Remember that. Don't write the acceleration alone. This is a M1A. Because these are all force. Okay, we are finding out the net resultant force. So let me call this as 1. This is for the M1. So similarly, you can do it for here. Here, which will be larger? M2G. So M2G minus T will be
M2.
correct. M2 into acceleration because M2 is moving down, right? We don't have to bother about others. Just to take only these two.
Equate the T.
Yeah, okay, do it. Equate the T. So what happens? So if from here T is equal to what? M1A plus G. Already we got the earlier answer. Okay. So then we put up the T there. So then M2G minus M1A plus G equal to M2A. Do it on a notebook and tell me what is A is. What's the answer?
A is equals to G times M2 minus m1
Mm.
divided by
m2 plus m1. And now substitute for the a here, you'll get back the same answer. Okay, so there's something important you have to remember. See, dimensionally, see, one of the things is whenever you are doing all this problem in physics, it's always a good practice to check the dimensions. Yeah. No, we have to check whether the dimensions of the left hand side and the right hand side are same. So let us see. The left hand side, what is dimension? Tension. Tension is nothing but the force. So right hand side also should have the dimension of the force. Okay, the force dimension is what? Mass into acceleration will be a force. Correct? Now see here. The 2 times mass. Okay. So now, so this is going to give one mass into acceleration. Okay, so what will be the dimension? Tell me the top of the dimension here. m1, m2, right? So 2 mass, that will be m square. And the gravity, acceleration due to gravity. What is the acceleration due to gravity? Tell me. Acceleration, na? Meter per second square, right? L t power minus 2. And then divided by, you are having what? This is mass, m, right? So this makes it what? m L t minus 2.
m1 L1 t minus 2.
So let us see tension. Tension is what? Nothing but the force. So force will be what? ma. Okay, use the formula for ma. So what is m? M is what? Mass, right? Mass into acceleration is what?
Velocity by time.
Distance by second. L t power minus 2. Are they both same?
Yes.
Okay, so in physics, always whenever you are doing, you should have, this is a good practice to check out the dimensions. That says whether the problem what you are doing is correct or wrong. Okay, good. So now we can see this is correct by dimensional. Here also you can check it out. Here the mass anyway it cancels off. So of course acceleration and acceleration. Okay. Because above you have dimension of mass. Denominator also you have dimension of mass. So dimension of mass gets cancels. So you have only acceleration on the both sides. So for this one. Okay. So with this I stop. So the next class we see about collisions. Okay, elastics and inelastic collisions. Let us see as we go along what are things we have.